happy to be here. I have to say that yesterday morning at breakfast when Araceli asked me if I could replace Dennis Sullivan, the obvious answer is no. Nobody can replace Dennis, but I will try to fill his time slot at least. And I guess I know that a birthday conference like this is really tough for Jack to listen to all the talks, so I hope I can say something that is okay for him to listen to and get a little bit of amusement. What I would like to do is talk about dynamics of invertible mappings. This is a topic that there haven't been so many talks on, like zero. And so I think I would like to give, well, I can't give a mini course here in the next few minutes. In fact, I can't give a micro course in the next few seconds, but maybe a nano course or a pico course or something. But I'd like to say some things just in general about dynamics in, well, if you want to have invertible dynamics in dimension, you have to go to dimension 2. So I mean dimension 1, as you know very well, that's, if I'm thinking here of polynomial dynamics, we've got this. If we want to try to make it something invertible, if we're trying to develop one of the approaches here that I'll keep referring to is you want to have parallels between dimensions 1 and 2. If you start out with this one-dimensional mapping, if you do this to it, if you add a second variable w, that makes the first coordinate invertible. If you put z in the second coordinate, that's an invertible mapping now, and it has a polynomial inverse. So here you have something, and you say, well, let's look at and see what the dynamics of such polynomial mappings is. But on the other hand, if you would have started out like with the identity map and added on some polynomial p of z in the second coordinate, you have a different automorphism. And in fact, the iterates in these maps, the dynamics is completely different between these two maps. The first map is quite interesting. The dynamics of the first map is quite interesting. The second map, the dynamics is quite tame. How would we approach this? Well, I mean, the idea is you have some very large group of polynomial automorphisms of C2. How do you sort out inside of this group what will be interesting to study and what will not be interesting to study? And I'm just trying to think of various approaches here, just like little word bites here. Your word of wisdom might be use algebra. In fact, the structure of the polynomial automorphisms is known. There's Jung's theorem is a starting place. And so how would we proceed here? You want to look at the degree of a mapping. Okay, so this is, I'm thinking here of algebraic degree, not topological degree. These mappings are all invertible, so the topological degree is always 1. But when I'm thinking of this as being a pair of polynomials, it has a degree as polynomial. And but one thing is that the degree doesn't work straightforwardly, beautifully. If you know the way you might like this to be multiplicative, but it's only submultiplicative. For instance, if you take a mapping and you take its inverse, if it's not linear, this will be bigger than 1, and so it's never multiplicative if you look at it that way. So what would you want to do? Well, this is not only, but the degree also is not a invariant under complex conjugation. And this is a situation that was studied in a paper that I've always appreciated very much by Friedland and Milnor, which this paper by Friedland and Milnor basically set the course for studying the dynamics of polynomial automorphisms of C2 because it told you where to look and sort of what direction to go in. So you have the complex Henon maps, which were the first map that I was showing on the previous page, except for certain reasons it's nice to write it the other way around. This is the, in other words, think of it as y going to p of y with then some perturbation to make it invertible. Think of it that way, algebraically for the instant. Anyway, so this paper of Friedland and Milnor contains quite a lot of results. One of them is this: if you are looking at mappings, if you take some mapping G, it's a polynomial automorphism, and if it has dynamical degree bigger than 1, the dynamical degree is the exponential rate of growth of the iterates, the degrees of the iterates, then in fact, in its conjugacy class, there are complex Henon maps that are conjugate to it. And let me see, the thing I forgot to say, we're running out of space on this slide here, the actual degree of this composition of Henon maps. You can see you're always, the thing of degree bigger than 1 is over here in the second coordinate, and when you're composing Henon maps, you're taking these polynomials p in the second coordinate and composing them with themselves. So one variable polynomials, the degrees multiply nicely when you compose them. And so when you have Henon maps like this, the Henon map, when you compose it, the degrees multiply nicely. And so, in fact, the degree of a composition of Henon maps is the same as its dynamical degree. And so what this says is if you take any polynomial automorphism, if it has dynamical degree bigger than 1, then in fact, you can represent it by composition of complex Henon maps, and those will have minimal degree in the conjugacy class. So that's one thing. And another, third in the same paper, is that you have two possibilities here. Possibility 1 here is the dynamical degree equal to 1 case. I don't know if you can remember this paper, it's been a long time. The degree 1 case is your mapping will be affine or elementary. The dynamical degree bigger than 1 case is composition like this. And in fact, what this paper does is to show that among other things, it shows that the elementary maps and affine, the case 1 is quite simple to organize dynamically, and so we're led to consider mappings like this when we want to study the dynamics. Now, companion result here is that also the compositions of complex Henon maps are exactly the ones, the complex automorphisms that have topological entropy bigger than 0. And here I should have said for all maps, the topological entropy is the log of the dynamical degree. So that would have, I could have said that. That would have been good. So what about Julia sets? Pursuing the analogy with the one-dimensional, whoops, excuse me, I hit the wrong button there. Sorry, where am I? Julia sets, that's what I wanted to be. Okay, so you can define Julia sets the same way you do define Julia sets for polynomials. And one thing that's an interesting result, so I'm a little bit, if you'll forgive me, I'm a little bit self-advertising. I would like people to read. There have been some papers written on complex Henon maps, and I encourage you to read them if you have time. And so the S in the BS series is John Smiley. So I just thought if I say once it's Smiley, then we've got it. Anyway, so when we're looking at Henon maps, we've got this Julia set J plus. And there says anytime you take any saddle point, it'll have a stable manifold, complex manifold. This will be a Riemann surface nicely, well, I don't know whether you consider it nicely or not, but it'll be sitting there inside of C2. And in fact, this will be inside of C2 as a dense subset of J plus. Okay? So this is to me it's interesting because it's a statement that holds for all possible saddle points. So they're all.
What is a saddle point?
Okay. I forgot, as I said, we haven't only been discussing dimension 1 in this whole conference. So a saddle point is a fixed point or a periodic point such that the differential at a saddle point has multipliers. One of them is bigger than 1 in modulus, the other one is less than 1 in modulus. And so there will be a manifold of points. The stable manifold will be the manifold of, actually the stable set is a manifold, complex manifold, and it's the set of points that chase the point Q in forward time. Okay, so in fact, these points converge exponentially fast to the point Q. Okay, so how do we envision Henon maps? I want to be talking about J plus, so that's our Julia set. Of course, there's also J minus. They're both J plus and J minus, but if I spend my time talking about J plus, if I wanted J minus, I would just take F inverse and look at that. So an early theorem in the subject here of Hubbard and Obersforth, Fornes and Siebeny, it says if you start with a hyperbolic polynomial, expanding polynomial, okay, and then you make the corresponding map like this, okay, then in fact, when we look at this intersection of the forward and backward Julia sets, this smaller set J, the dynamics of F on J, well, you have the dynamics of the polynomial on its Julia set, and you take the projective limit. Okay, so you take the set of infinite orbits, and that's this. I was going to show you a picture, but the picture I drew was just sort of terrible, so I'm not. Well, I'll put it up here, but my apologies because I'm not very happy with this picture. But so this. Okay, now how are we doing here? Okay, so. The more I look at this picture, the less I like it. Let me just take this picture away. I don't think this illustrates anything very well. Sorry. I tried drawing a picture, but now I've failed as an artist. I'm sorry. So, in fact, these, if you take a small perturbation here of a one-dimensional polynomial, you can show that this automatically is hyperbolic in the two-dimensional sense. So hyperbolic in the hyperbolic in the one-dimensional sense means that you're uniformly expanding on the Julia set. Hyperbolic in the two-dimensional sense means that you have an expanded direction, the direction that's over the set J. Here you have a direction that's uniformly expanded, and you have a direction that's uniformly contracted. So it's easy to see that. Oh, that's supposed to be a delta x. Sorry about that. That's supposed to be a delta x there, and that's supposed to show you that in the second, in the x direction, you've got strong contraction. So anyway, so it's easy to imagine this is hyperbolic, and so since I'm trying to stand in for Dennis, let me just say it this way: there's a picture for axiom A maps that Ruel and Sullivan developed, and if you have a hyperbolic Henon map, then it automatically satisfies this Ruel-Sullivan picture, which is nice. However, the question of hyperbolicity is very nice because you there's a whole theory of hyperbolic mappings. It's something that has been very much developed. But in the case of Henon maps, how can you actually tell if a Henon map is hyperbolic? And so I want to emphasize this question because in the one-dimensional case, when you have a rational map or a polynomial, you know there's a direct condition for hyperbolicity in the sense that all the critical points are attracted to single orbits. Okay? And there just isn't any known way of there's no nice criterion in dimension 2 that's known yet. Okay, so that means like if there are some active minds in the crowd, then if you can come up with something, that would be just great. And also, especially if you consider instead of just trying to describe hyperbolicity in general Henon maps, it would be very interesting to have some special cases, there's some more special mappings that within that subfamily could you characterize hyperbolicity. So I'm going to be posing a few problems here. What I'm going to be doing is sharing ignorance with you. And by ignorance here, I mean that we have a certain amount of knowledge. I mean, in the complex dimension 2, we know of a certain amount, but in fact, there's a lot more unknown than there is known. And the ignorance here, by that I mean the boundary of knowledge. Okay, it's just sort of where you're trying to push beyond what you know and what you don't know. And so I'm encouraging, like this question here, that would be very interesting if somebody could do that. In the end, I'm going to be saying that the J plus can never be smooth. Let me say here what it cannot be here. It cannot, so case 2 means, did I erase a transparency somehow? Okay, I think I left something out here. Oh yeah, sorry, it was here and I forgot to speak in words here. Okay, as we saw from Friedland Milnor, there are two cases. There's the affine elementary case and there's a Henon case. And in the affine elementary case, when you go to define this Julia set, it might be empty even if you just have some affine map that translates away to infinity, or otherwise it'll be an algebraic set. Okay, so that's I'm not interested in discussing J plus in the case 1, but in the Henon case 2 here. First thing is it can't be a manifold of real dimension 2, okay? Because you know that Henon maps have infinitely many saddle points. Each saddle point is inside its own stable manifold. Distinct saddle points have disjoint stable manifolds. And so you know that there are at least 2 manifolds there. Let me see what else. Anyway, it just can't be. If J plus is going to be a 2-dimensional manifold, it has to be one of these stable manifolds, but it can't be. So, but it could be a 3-dimensional manifold. The theorem I was saying before, Hubbard over Sforna-Sibony, if it's the case that you've got a Jordan curve here. I've got my X here, good. If you have a Jordan curve, then in fact, their theorem says, in fact, the J plus will be a 3-dimensional manifold that's laminated by complex disks, embedded images of the complex disk. And if you take the cross section, if you take a transversal slice of J plus, whatever I've written J plus, if you take a transversal slice of J plus, it'll look like the one-dimensional piece of the one-dimensional Julia set.
Eric, can you say what that means? Do you mean there's a semi-conjugacy to J, or what does it mean
not respecting, let me see. So the point is that J plus, let me get back to get back to the failure of art here. So, so here's J plus, and the Julia set is written there in orange, and I can embed that in there. Let me see. I've got the big man here. I don't think, so I believe you can basically, this is an unstable manifold coming across, so this is a complex manifold, and here it slices in J plus, and this is quasi-conformally J sub p. Now the dynamics is complicated because the dynamics is just, we were looking at the projective limits, so this thing that I've written, this three pink zigzag, ziggly things, in fact would be some kind of solenoidal looking object. And so your mapping is going to be sort of wrapping that solenoidal guy around, and at the same time it's contracting in with these stable manifolds. So so it's a little complicated to say.
What I'm asking is there a map from J plus to JP?
No.
But you've written it locally as JP intersect U cross delta, so you can project to the first vector.
So let me see, sorry. So JP is a piece of Julia set inside of C. I just want to take a little piece of a model. So that's like a little pattern. And so a little piece here, that'll look like, I've got the J minus coming along like manifold with the cross-section being a Cantor set. So locally, all these Cantor, point components, all those things look like disks, and the way you intersect the Julia set J looks locally like this. The local product structure is a little complicated to explain because it's not global. I mean, you want it to be global. I believe you want it to be global. I want it to be global, but it isn't.
Okay, so another way of saying it is that if you cut off at G plus less than some epsilon and delta is sufficiently small, then there is a map to the Julia set, which respects the dynamics, and which is quasi-conformal on each slice.
But that's a...
But that you have to restrict because these stable manifolds are all dense everywhere, and they end around and come back and so forth. In some not all that complicated way, but still totally forbidding from actually being a global map on the on J plus.
Right. So at this stage, actually the same paper by Fornes and Sibony, they observed, I changed H to F, sorry about that. They observed that generically J plus is not going to be smooth, and certainly at this stage of the game, back in these days, everybody assumed that it was never smooth. I mean, nobody ever imagined that it was smooth, but it's an issue of how do you prove it's not smooth. So I want to have I've got about 10 more minutes here to do a certain thing here. And so let me just make some discussion here. If you're pursuing the analog between the one-dimensional and the two-dimensional cases, you could say, well, what is the dynamical behavior on the Foto set, since the Foto set is sort of the easiest thing to get your hands on, maybe. Here, just to remind you, the Jacobian here is a constant. You have a natural dichotomy in the dissipative and conservative maps. The dissipative case is volume contracting. If I had volume expansive maps, I would just take F inverse and discuss, then I'd start discussing it. So the standard problem that anybody would ask would be, can you have a mapping with a wandering Foto component? Okay, and I think the question is, so it's known, it's a theorem that if your mapping is hyperbolic, then there are no wandering components. But what about other classes of mappings? I mean, it's interesting. I mean, even if there is a wandering Foto component, it would be very interesting to know if for special classes of maps, there were none. So in connection with that, there's a very interesting paper by 5 authors. So I guess since I've listed them, or Estor, Dujardin, Peters, and Ricey, and saying that you can have a polynomial map from C2 to C2 is non-invertible, okay, but it has a wandering Foto component. Extremely simple map, but to be able to prove that there's a wandering component is extremely clever. So it's not a short paper. However, their map, you would say, well, why don't you take this map and monkey with it, fix it up, and make an invertible map with a wandering Foto component. The whole key to why this map works is it has a parabolic fixed point. Okay, so it's all the interesting dynamics involving the wandering Foto component takes place at a parabolic fixed point. If a Henon map has a parabolic fixed point, that means you've got a fixed point and both multipliers of the Jacobian are 1, then delta is 1 and it's not dissipative. Okay. So, what about the other case? You have the 2 components, take a connected component. If it's not wandering, some power of f will take omega to omega, so let me just assume omega is taken to itself. Then one theorem, so I put numbers here to hope that maybe you'll look at that paper. So that paper has a classification. So I don't think I need to define what recurrent means because it's either going to be recurrent or non-recurrent. But I mean, what I meant was that, how am I doing? Am I doing that a little bit? Okay, so you have 3 kinds of basin. So if your Foto component omega is recurrent, it's going to be one of these 3 kinds of basin. So the first kind is a basin of an attracting fixed point. Okay, just a standard thing you all know. The second thing is there can be some embedded complex disk on which your mapping is rotational, so like a Ziegel disk inside of C2, rotating. Okay. And then our Jacobian is less than 1. Is basically an isometry moving around, moving the disk around, and so you have another attracting direction. So you have a whole basin of points attracted to this disk. So that's one possible Foto component. And the other Foto component would be you might have some kind of invariant ring, like a Hermann ring, and then you'd have the basin attracted to that. So these are 3 possibilities in the dissipative case. What I think is a very interesting problem, probably very hard, is can there actually be an annulus? Can you actually have case number 3? Case number 1 and 2 are different because both of them have fixed points. Case number 3 has no fixed points. The annulus is just moving around without fixed points. I mean, it's an irrational rotation, and then the basin is attracted to this annulus. So that is part of the answer to what happens on the 2 components. Another thing is a more recent result of Lubitsch and Peters, and that is suppose you are in the other case, where the opposite of this case, suppose you have a 2 component that's not in that case. If it has a specific amount of dissipation, then in fact it's the basin of a semi-parabolic fixed point. So I don't have time to discuss semi-parabolic right now, but that's a very interesting sort of conclusion to draw. But clearly you'd like to know what about the general case. Okay, let the dissipation be this dissipation. Okay, that's the dissipative case. What about the conservative case? Okay, suppose you are looking at the volume preserving case. Again, sort of the starting point, we start back to Friedland Milnor. They said that if you have the volume preserving case, then the intersection, so the only place the two components could be, I should say, there is the component at infinity, which is not what I'm talking about. I'm talking about the two components that are not the escape locus at infinity. So this set here is inside of some bidisk of radius r, and so the conclusion is if you have a component of here, so it's possible to take any Foto component, then it has to be periodic because your mapping is preserving volume. You've got images. The images are either disjoint or they coincide, so they can't be disjoint forever. So because you only have finite volume, so the conclusion is that it has to be periodic, which means in the conservative case there are no wandering components. So suppose we look at that case. Now, if we want to look further, we can take the sequences of iterates of f restricted to that component. I'm going to again assume that I've passed to some power, some finite power, and I just have a component that's taken to itself. And so if you look at the limits, take the closures, okay, you're going to get something that's going to be a real torus with the rank either 1 or 2. And so in that case, omega has got a torus action, so it's a rotation domain, and it'll either have rank 1 or 2. And so let me point out just a little bit more here. You certainly can have such domains, okay, just from what we, if you take a couple of numbers with modulus 1, suitable rotation numbers, they have to be without a resonance, suitable, but there's lots of choices. And then if you just construct any Henon map that with a fixed point and this linear part of the fixed point, then it can be linearized, and the conclusion is if you can linearize your mapping, then you certainly have a Foto component associated with it where you can linearize. And so you have a Foto component, period, okay? Conversely, suppose you have any component of the interior here that's, so we knew that everything ultimately is periodic, and so we can just assume it's taken to itself. If there's a fixed point, then it's a standard argument to show that in fact you can linearize at the fixed point. It's because it's inside the Foto set. And so, to me, it's a very interesting question. Do Foto components in the volume preserving case, do they always have fixed points? In other words, do these things always arise somehow from linearizing the mapping at a fixed point? And another question here. I should sort of move along here. I'm sort of wallowing too much in my ignorance. And then the last thing is, just in terms of language, in the one-dimensional case, whenever you have a rotation domain, you talk about it as being a Ziegel disk, because if it's simply connected, it's uniformized by the disk, or else you could talk about Hermann ring, because it's uniformized by a ring, okay? And so it's shockingly ignorant that we don't know any case of any component. What would it be if you uniformized it? Whatever in two-dimensional complex analysis, the word uniformization doesn't really have exactly the same meaning, because you take a generic pair of domains in complex 2 space and they're not bi-holomorphically equivalent. take a couple of random domains, and they're not the same, but you know, the question here is, if you took one of these components that is probably going to have a very funny boundary and be embedded in some way, can you identify it in terms of some reasonable domain, like a bi-disk or a ball? Personally, I would think that both of these never occur, but it'd be very useful to know as a fact that they don't occur. Anyway, so let me just move forward here. I guess I've got 3 more minutes and then I have to actually get to the topic of my talk. So this is the escape region. There is a green function that is very, very useful, and orbits escape. So if I look at a saddle point Q, I can uniformize it by some holomorphic entire function here. And there will be a functional equation like this. So this will be the unstable multiplier of the differential of f at the point Q, that'll be that beta, and multiplying on the inside by beta is the same as composing by f on the outside. And the connection, oh, did I screw up? Oh, sorry about that. Okay, thought I fixed that. Okay, so here I'm looking at G plus, and here I've multiplied with the multiplier on the inside. Okay, so that's not supposed to be there. That's the same as composing with f on the outside, which multiplies the green function by the degree. So this second beta isn't supposed to be there. Sorry about that. It's my mistake. Okay, I was going to spend a little time talking what do these things look like. There is the Hubbard picture, which means that if I look at this uniformization and pull back the green function, okay, we can make a picture. And the picture is very analogous to the picture that's made in dimension 1. And so here is an example of some mapping. Okay, so this is, in some sense, a perturbation of a one variable mapping z goes to z squared minus 1. A very familiar map. But it's not exactly a tiny perturbation. It's a little bit bigger than that. So you get, in this case, when you draw pictures of slices, so we're looking at a slice of the Julia set, you get something that's going to be self-similar. Okay? And this is for one saddle point, and this is the picture you get looking at another saddle point. And I have a picture like this, so this is sort of a schematic picture to explain what's going on. Here's one saddle point that was supposed to be this one, and the other saddle point will be like that one. So we've got the one there in the middle, and these are 2 saddle points. And this black line is a stable manifold, and that black line is another stable manifold. And the point is that the features you see locally with that saddle point are displayed densely throughout these pictures, or the boundaries of these pictures here, because they're connected by the saddles, the stable manifold. And so if you want to see this stated more clearly as a theorem and proved, then you can look at that paper. Okay, so I need to rush forward here, so let me just skip some stuff. And so the thing I want to consider now is the possibility of smoothness. Okay? Now, when you consider the one-dimensional case, you have got a couple of smooth cases. You could have z goes to z squared. Julia sets the circle. And in fact, all the multipliers are 2 at the end. If you've got the Tchebyshev map, the Julia sets interval, and your multipliers are plus and minus 2 to the end. The point here is that you've got all the same multipliers. I mean, all the periodic points have the same multipliers, and here you've only got two choices for the multipliers, except the end point, except for that guy, all the other ones like that. And so you can ask, well, what about higher dimension? Well, Tchebyshev maps in higher dimension are not invertible, but there are such things, and people have discussed them. In certain cases, and you have a very nice-looking Julia set. I mean, they're semi-algebraic, so they have cusps and things. But you can ask, well, could you have such a thing? You could look at it. Is there some sort of Henon map that is better than all the other Henon maps in some sense? Like z squared in dimension 1 has got a nice circle, as Julia said. And so, in particular, if there was a really good one, you'd say, well, maybe there could be something with a Julia set that's going to be C1 smooth, but as you know the answer already, there won't be. So this is I don't just put K there because Kim is not a unique identifier in Korea. But John Kim, collaborator here, this is a theorem with her. And that says if you take any of these mappings, composition of general Henon maps, the Julia set is not going to be a C1 manifold with boundary. And so what's a manifold with boundary? Well, just plain C1 means you have a defining function. We're not talking about a 3-manifold inside a 4 space, so you have a simple defining function with a non-vanishing gradient. And a boundary point means you have a second, the first function R serves to define the surface, and the second function S serves to cut it off. And so that would be what a manifold with boundary is. So the first thing is that if you have such a thing, C1 manifold with boundary, if J is that, then it can never have a boundary. Okay? So let me see, how is this going to look all right? Is that visible or not visible? Okay, so the thing is this M, that's supposed to be, I'm thinking of this J plus as being a surface and the M is the boundary. Okay? And the argument is that if there is a boundary, then G plus has to be a proper exhaustion. Okay, in other words, if I look at this region, this is the set where y is less than or equal to r, then y less than or equal to x. If I look at this region, I know that J plus has to lie in that region. If M, if M is the boundary, I know that G plus is a proper Fourier-subharmonic exhaustion function out at infinity, and so I've got some Riemann surface M, and it has to be a closed submanifold, okay, because it might have a smooth manifold with boundary. M, where am I? M is a Riemann surface, and the restriction of G minus to M will be a subharmonic exhaustion. It's harmonic on the set where G is strictly bigger than 0. And so what I know is that when I compose with F, I know that there can only be finitely many components because the first part of the argument says that all the components have to come through this little polydisk, and so there can only be the boundary in that compact set. There can only be finitely many components. So I can assume that one of these components is invariant under F, and so I use this functional equation. When I compose the green function with F, the green function divides by the degree, so that tells me that another fact about the green function is it's Fourier harmonic outside of this middle bidisk, and so that tells me that this when I take this thing to the inside, it has to be harmonic, but except on some fixed point. In other words, everything is brought in. I've got some automorphism of M0, and so there can just be a fixed point, and in other words, this is harmonic everywhere except for the place where it reaches its minimum, but that's not possible. You can't have an isolated singularity like that. So there can be no boundary. So this means then that J plus is a closed submanifold of C2, which means it is going to be orientable, and it's going to locally define, let me see here. So it's going to be orientable, and so I know that it has to have at least two components in the complement, and so I know that there is the escape locus, and there has to be some interior of K plus for the other side. Okay. And so so Friedland and Milnor showed that if delta is greater than or equal to 1, K plus cannot have interior. So this tells me that we have to be in the volume decreasing case. And so the next thing is that there's going to be at most one fixed point. In other words, in the interior of K plus, there can be at most one fixed point. Because if you have a fixed point, then it's going to lie inside of some recurrent Foto component. And it's a theorem that such recurrent Foto components, their boundary is J plus. Okay. So we have a smooth surface. One side of the smooth surface is the escape locus, and if you have a fixed point on the interior of K plus, its Foto component the boundary of that Foto component also has to be J plus. So you've only got room to have, since you have a smooth surface, you only have room for two things, and so you can only have one fixed point.
Where are you using the hypothesis that J plus is smooth?
To say, I'm just using that it's a three-manifold. In other words, so it's smooth, so it'll have two sides.
That's true for just a topological.
Yeah.
So far this is true about you've described exactly when J plus is the topological bound.
Unnecessary condition. Delta has to be less than 1. Yeah.
It has to be recurrent, and it has to divide C2 into two pieces, and one of them has to be the base of K. One side must contain
The base of infinity.
yeah.
And then the other side, right? So you can have at most one fixed point. And so the point is then by some discussion here, which I think I'm running out of time here, then all the other fixed points have to be in the surface J plus. So inspecting here, we can show that the other points in J plus have to be saddle points. So now I want to claim that if you have a saddle point, then I want to uniformize the unstable manifold. See if that looking okay or not. Okay, so what I've drawn here is C, and this is supposed to be the copy of C that's the uniformization of an unstable manifold. Now, what I know is that I have a multiplier. Okay. I have a multiplier beta, and this, let me see. This unstable manifold has to intersect J plus transversely at a saddle point. And so this has to be a C1 curve. Furthermore, it has to be scale invariant. There's some number that scales it and leaves it invariant. So the number's got to be real, and when I claim the number has to be deep. And so, what's the argument here? Okay, so I know that when I take G plus, and inside when I scale my point zeta out by multiplier beta, that's the same as G plus getting multiplied by the degree, okay, which I call D, that's the degree. And so the point is here, since this has to be C1 and scale invariant, self-similar under the multiplication by some number beta bigger than 1, it has to be straight. And so I know that this green function here is some function that's positive and then 0, and then, you know, it's either, on each side it's either going to be 0 or it's going to be some constant like times the modulus of imaginary part of z. And so, since I know that when I multiply inside by beta, I pull out beta. And over here, so I pull out beta there. And over here, I'm getting the degree. So the conclusion is that the multiplier has to be the degree. So, I have a lot to do in 5 minutes. So in fact, the point here, it turns out, there's this actual number is not the thing that we're going to be using. The point is there can be one fixed point that's in the interior. All the other fixed points have to be in J plus. And so the point is all the other multipliers are the same. Okay? So I want to show that you cannot have a Henon map such that with one possible exception, all the multipliers are the same. So now I will go back to algebra, which I hope Jack finds amusing. We want to show that this can't happen. So how do you know that? Well, I want to unfold parameter, the dynamic of space. Okay. So here, so I'm taking my composition of n complex Henon maps and just writing them as going from C2 to C2 to C2, but I'm using different variables at every stage. I'll leave this up here to remind you the definition of a Henon map. And then here, okay, I want to keep this, I want to be using this equation phi sub j. Okay, so with Henon maps, okay, I know that I know that jy plus 1 is the same as yj. Okay, that's just a feature of this map. And so, in fact, I can forget the x's and just use the y's. Okay. And so, so if I look at these equations, okay, if phi1 through phi n are all 0, that means that I'm looking at the y-coordinate, and the y-coordinate corresponds to an orbit. I mean, I'm looking at y1 through yn. If all of these functions phi1 through phi n vanish, I know I have defined an orbit. And so I want to say, so the condition being a fixed point means that we're in the 0 locus of the phis. So we want to set up an algebraic geometry formulation of this. So we want to describe the differential. Okay? The differential is the product of these things. It's simple enough. And the condition for the multiplier to be lambda is just the characteristic equation. And so the lemma that's very, very useful, you can see that here you're multiplying some polynomial of yn through a polynomial of y1. So all of these things appear at most once. you could have all of them appearing, which that does happen, but then it turns out the summation for all the other things is taken, you go from n to n minus 2, so all this other stuff involves products of length less than or equal to n minus 2. So this is now a problem in algebraic geometry. So I'm saying the simplified theorem here. Suppose all of my fixed points are in J plus. And that means they all have to have multipliers lambda. So that means they all have to satisfy this thing equal to 0. Remember this thing here is the characteristic equation here. So if a point, if phi at a point is 0, that means it's that means the multiplier has to be lambda. And so we're saying this is all the fixed points, okay, within our unfolded dynamical space, and we're saying has to lie inside that variety. And so we're wanting to say that they're not all inside that variety, so we're wanting to say that this does not belong to that ideal, which means, sorry, I'm missing a not here, okay. Phi being in the ideal means that phi is written that way, okay. So we want to say that it actually is not in the ideal, okay. So, in fact, so this is sort of clear if you look at the definition of phi. Okay. This is a product, so y1 only is to degree d1 minus 1, yn is only to degree dn minus 1, and so it's not divisible by any of the phis. So this one is clear that we cannot have this. However, the thing is, if one of the fixed points is not a saddle with multiplier lambda, then it would satisfy this. In other words, we have one escape, so we need to show that this can't happen. So, how do we do that? Well, there's the multivariate division algorithm, which is just this. The idea is you can try, you want to see if something or other is in the ideal. So you can try dividing, and there's a sort of an algorithm for this. You can keep dividing, and then the question is, do you get a remainder at the end? Okay. Well, what I've written down here as an algorithm is not actually a deterministic algorithm. I've told you things you can do, but I haven't told you precisely which thing to do. You can do it sort of in different orders, or make different choices, and so the R is not uniquely defined here. However, this is a problem, this multivariate division algorithm problem is a thing that if you use a Grobner basis, then you will get a unique answer. Okay, so let's do that. And so let me, so I think I really don't have time to linger on this transparency, but there are a lot of equivalent definitions of Grobner basis, but the long and the short of it is, if you have a Grobner basis, you have a very specifically defined division algorithm, and you go through there and you get a remainder, and the remainder is either 0 or it isn't, and that's the answer to your question. So let me put it this way here. So you can define, okay, just recall that's the degree, and we're going to use graded lexicographical order, which is defined here, but there are actually, if you think about it, there are only sort of 2 orders you could even think about, and this is one of them. And so the lemma here is that this particular set of polynomials is a Grobner basis, and if you, so the theorem is this: if we take anything that's a composition of Henon maps with n at least 3, then this thing is not in that, so this thing here, so this is the condition that all the multipliers of the fixed points, except possibly one exception, one escape here, are going to be lambda, be the same, for some, for any lambda. This, so we have this condition. Well, this is not the thing, and you can show by dividing by phi1, phi2, take this left-hand side, divide by phi1, phi2, and phi n, you get something or other that when you look at this, you see that when you go to apply the division algorithm, nothing divides. Okay? In other words, when you're looking to divide by phi j, for any j between 3 and n minus 1, you have to divide by yj to the d, dj, you have to divide by the leading term, but nothing here has high enough degree to be divisible by this guy. So the conclusion is that if you have at least 3 of these guys, then the multipliers, all multipliers except 1 can't be the same. So the fact that n is greater than or equal to 3, if you just have one complex Henon map, just take f cubed, and then you're talking about points at period 3. But so if you just have one map, take f cubed, and then you're done. So this is what I wanted to say. Hope it was okay.
Questions? Yes?
I mean, there was the transition to this algebra bit at the end, and I just sort of lost sight. This was a solution to something, right? So could you just say again what this is a solution?
Okay.
Now you don't need it.
So what we showed earlier was that if you have a smooth Julia set, if you take any saddle point inside the Julia set, it has a pair of multipliers. The expanding multiplier has to be d, and the Jacobian is delta, so the other one has to be delta over d. And so this was an algebraic discussion saying, so you're looking here at all fixed points. Okay, so you've unfolded dynamical space here. So you describe a fixed point as y1 through yn, an n tuple, indicating its orbit as you go through f1, f2, f3, up to fn. And then, so you have a thing describing all the fixed points. So you have a zero locus, and you're wanting to show, and then you can compute the condition that all the fixed points have the same multiplier. Okay, and then what you show is that well, you want to show that this is not possible. Okay, in other words, the left-hand side, this is saying that this would be the condition that all the fixed points have the same multiplier, and this y1 minus alpha allows one of the fixed points to escape, to not be meeting the criterion. And here, this is the condition of being a fixed point. Okay? So you want to show that this is not possible, so you just take the phis, okay? And if we show that phis are a Grosvenor basis, and so when you do the multivariable division algorithm, you see that when you go through it, you're going to have a non-zero remainder. So that's the argument.
Any other questions? I think you have something left.
Yes, I want to say the most important thing.